Chapter 5.5 Stationary waves. 1. Stationary waves on a spring. Traveling waves travel from one place to another. Stationary waves only set up vibration, but the vibration does not travel. Let's take a look of the following video to see how stationary waves are produced. Experiment 5H. Stationary waves.
Fix one end of a long spring to a rigid support. Stretch the spring. Send a pulse along the spring. What happens to the pulse when it arrives at the fixed end? Flick the spring continuously. Slowly increase the frequency. What kind of wave pattern can you observe?
A stationary wave on a spring appears as vibrating loops. The points that are always stationary are called nodes. The points that vibrate with the largest amplitude are called antinodes. Still remember nodal lines and antinodal lines in interference pattern? The separation between two successive nodes or antinodes is half of the wavelength. 2. How is a stationary wave formed? In the above video, the stationary wave is formed by a wave with its reflected wave. They interfere when they meet. They can surely interfere because they must be coherent. For a piece of string to set up a stationary wave, the two ends must be nodes, because they are fixed in position. The little vibration of the vibrator does not matter. So there is a limitation to the wavelength of the stationary wave that can be set up. The limitation is called boundary condition. In short, the length of the string L equals n times lambda over 2. And hence only those corresponding frequency of wave may set up a stationary wave. In general, a stationary wave can be formed by any two coherent waves of the same amplitude traveling in opposite direction if the wavelength matches the boundary condition. 3. Characteristics of stationary waves. Now let's examine the particle vibration of a stationary wave. Experiment 5I. the transverse stationary wave model.
Set up the transverse stationary wave model on an overhead projector. Project the image of the model on the screen. Stick several pieces of plasticine evenly on the wire. These plasticine pieces represent the particles on the wave. Observe how these particles vibrate. Do the particles vibrate with the same amplitude and period? What can you tell about the phase relationships of the particles?
In old days, without computer simulation, the transverse wave model was used. It shows clearly the vibration of particles in a stationary wave. A. Amplitudes of particle vibrations. Transverse stationary wave appears as a series of vibrating loops. You can see particles vibrate with different amplitudes, but with the same frequency. B. Phase relationships of laboring particles. In a stationary wave, all particles reach their maximum displacement at the same time. Particles vibrating within the same loop vibrate in phase, but in antiphase with the particles in laboring loop. C. Transmission of energy. Energy stored in a stationary wave. A stationary wave does not travel, so it does not transmit energy. Table 5.5a compares traveling wave with stationary wave. Please read it carefully, line by line. Example 8. Particle motion in a stationary wave. You have to determine whether the wave is stationary or traveling by referring to the motions of particles E and G, both moving downwards. As they are in the same loop, same phase, if you can't tell it is a stationary wave, you will get all wrong in this question. Try check point 7, please.